Yeah, so what's the square root of 48 roughly? Almost what? 7. Good. Square root of 49 is 7. So I know that's going to be the turning point in my list. Yes? So let's do an example. I'm never going to come up with an example that works. If I do, I'm going to be amazed. So let's try 56 and 21. 20 what?
9.
No, that's no good. Sorry. This is definitely not going to work. So let's try 56 and it doesn't matter, Jeff. 16. Sure, it's not going to work. Either way I look at it. What are the factors of 56? Well, the square root of 56 is roughly between 7 and 8. What does that do for me? Does anybody remember? Tells me where to stop at those I'm trying to make. Remember the way the girl did it in the video? 2 times what is 56? 28, good. So what else goes in? What goes into 28? 4. How do I know 3 doesn't go into 56, by the way? 5 plus 6 is 11, no good. 4 goes in. How many times? Here's a cool trick. Isn't 2 times 28 56? Yes, yes. So if I steal a factor of 2 away from this, 4 times 14, okay, good. Does 5 go into 56? No. Does 6 go into 56? No. 7. What's 7 times 8? Good. So we got to the turning point, yes? Now, what is, already it's going to die. If I just take the middle ones, what is 2 plus 4 plus 7 plus 8 plus 14 plus 28? Whatever it is not 16, yes? So they're not going to be betrothed. So to be betrothed is really funny. The factors, the inner factors, excluding the here, these guys, if these factors add up to be the number, and it works the other way around, then they are betrothed. Or betrothed, sure. Is that like a majorly important idea in mathematics? No. It's just a problem that shows you, hey, this factoring stuff leads to weird little relationships between numbers. Okay. Okay. Anything else, guys? Like dwindling a little class. Attendance has been weird this week, but you know,
When
things
we
happen.
do the betrothed thing, though, we wouldn't do the 1 plus 56, we would skip that.
Yep. So I didn't really talk about this. Proper factors mean every factor except one in the number itself. So you could say that a prime number is a number that only has improper factors, one in itself. Yeah. Hey. All right. Anything else? So I think I need to adjust something. I just was working on updating the homework, kind of like timeline. Let's see. I had made an incorrect memory of, I think our last test stopped at section 4.3, is that right? This is one thing I didn't keep a note about, was where I stopped. Where I started, where I had the test go up to. I don't think 5.1 was on the last test, the divisibility stuff. Okay.
It was, there's no dividing.
So let's make this quiz. So I'm gonna update this. I'll put this up in Canvas. I'll change it. This is an updated kind of like timeline sheet. Just because we're sort of a little behind, I just want to kind of update some stuff. I'm gonna push the test back. And it's going to go from 5.1. I'm probably going to push it, I'm probably going to move it up in here somewhere. So I'll work on this. I just had forgotten that 5.1 was not on our last test. The next quiz is gonna be 5-1 through 6-2. That's gonna be on Tuesday. So the next test, I'm pushing it back a week. What's kind of nifty is Past Jeff decided to not even include April 30th as a class day on the first iteration of this, so I had an extra day just to work with, so that's kind of nice. You guys all with me, so I'm really happy I didn't make a bunch of copies of this now. The most important thing for you to understand is the next test will be May 2nd, and the next quiz will be next Tuesday. Okay. And then I'll work on the details when you pad up on Canvas. None of the homework has changed. We might have to, we'll see. We can make some adjustments if we don't quite catch up. We'll see.
Ours is a little different than
Huh?
Or am I wrong?
Yeah, of course, this is an updated one.
Oh, that's the updated.
Yes.
Oh, okay.
Well, I'm gonna have to update the update because
was
I had,
so lost. Okay.
Yeah, it's like,
yes, so like, yeah, so this is definitely not the same as the first one. And then I'm gonna update the update because I had forgotten 5-1 needs to be in there too. Yes,
is May 21st our last day of school?
for us, yes. Yeah.
Basically that Friday, so
Say again? Well, that is the last day of all classes. This will be the last day of our class.
Oh, but so I won't have a festival for that Thursday.
Yeah, yeah, you can celebrate if you want to. I won't take it personally. Alright, let's get all this stuff up here. So I put this up on Canvas, I'll adjust it and then put the newly updated one up there. Again, the most important things are the quiz on Tuesday and the test is gonna be moved basically one more week in our future. So what I wanna do is, today I'm gonna talk a lot, so just be ready. I'm gonna finish up chapter 6, we're gonna look at a few videos. I have to leave a little early today because I got my beautiful eye surgery happening. Yay, that makes it sound worse than it's supposed to be, like a few minutes and then they shoot lasers in there and nifty things happen. So I will make very sure, I wanna draw like a Sharpie. This eye, so please to God.
Drawing opposite eye.
Huh? Yeah, don't do anything to my one good eye. If I do this, I'm done. Okay. So we are in the middle of talking about everybody's favorite topic, fractions. Last time I got to play with the manipulatives, they'll come out again at some point. Not today. Today is not playtime. We will watch some little dudes and little dudettes working on some stuff here in a bit. Oh, let me keep myself straight. Yes.
Wait, is it final everything we've learned?
Yeah, final's cumulative. Cumulative. I love that word.
Like that.
Okay.
The word makes you sound drunk. Cumulative.
we'll get like a review type of thing before that one. Okay.
Yeah, of course. Yeah,
Like, dude,
I have practice finals with practice final answer keys, just like every other test. Yes, I like it. And just to remind you guys, we don't have more time for the final. The final exam, we get the same amount of time as we always do. So it's just gonna, I'm gonna pretend like everything could be on there. Will everything be on there? No, because otherwise that would be a 3-day final exam.
Is it like as long as a regular test though, or is it?
It has to be, because we don't have any more time than normal.
Oh.
So it'll probably be one question for each chapter.
Maybe, we'll see, unless I have like some favorites. And then I have more.
I'll be a favorite, no.
Everything.
No, I
is
mean
mine.
favorite questions, favorite sections.
I know.
So,
Everything is mine.
all right, guys. Let me ask you this: can you represent for me using a rectangle 1/4, like a straight across the way? Oh, yes.
3 lines.
Okay, 3 lines. Generally, those are equal. And shaded 1. Okay. now represent 2/3.
Possibly in the middle piece.
So now there's going to be 2 lines, and 2 of them are shaded. Okay. Now, what would I do if I needed to try to add these together? How could I do that visually? What's the issue with sort of just putting these 2 here, which is something that you could tell a student would think that they're allowed to do? You guys all with me? Yeah.
You would need to get a common denominator.
So, if I break both of these up into how many parts? 12. So if I break, if I break each one of these components up into 3 parts, yes? So I do 2 lines in each of these. So this is now representing 3/12, which we know is true, yes? And if I do the same thing here, but now I'm going to have to break each one of these up into 4 parts. So now a student could say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 12s. 8 12s. If I could just, this wasn't shaded. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why do I keep getting 10? Let me do this one over again. Poor little dude. 2/3. And then break each one of these. Yeah, it should be 8. My poor little. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2,
Yeah, keep getting
4, 5, 6, 7, 8, 9, 10, 11. 11. Yeah. Yeah. Okay, 11. I just wasn't shading all the way over in the last one. Okay, so if you had a little computer generated thing, that'd be much better. Okay. I just wasn't shading over in the last one.
Draw them like that.
No, you don't. In fact, one other way you can do this is if you had 1/4. Now this one gets a little bit trickier, but if you had 1/4, I can then break it this way, of course, and make 12ths that way. And then 2/3, if I did it, did I do that right? Today is gonna go well for you, Jeff. So if I have 1/4, okay, there we go, 1/4, and then I break it this way in 3rds. There it is, Jeff. Now it's 12. If I have 2/3, I go like this. And then I break it this way in 4ths. There we go. Yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. Okay. Could I do something? This is going to be a little better, thankfully. Could I do something similar for multiplication?
Yeah.
So just to remind you guys, 3 times 5 was like that, 3 times 5, and then if you count, and you get 15. If I want to do, for example, let's just do 1/4 times 2/3. Here's what I'm going to do. Shading is going to become part of the problem. So this way represent 2/3, right? So this will be, 1/4. So this way represent 1/4. And then this way represent 2/3. Let's see how this works. So if I do, and I take 2 of these, so that is 1/4 of 2/3. So if I draw 1/4 this way, so there's 1/4, and then I take 2/3 of that. So it's where the cross hatchings is, where you shade twice. So what is this? 2/12, I love it. And of course, now here's what's really nifty about this. If I look at this as one piece, do you see how there's 1, 2, 3, 4, 5, 6 of those? So how many of those pieces I've shaded? 1. So that is another way to show that 2/12 reduces to 1/6 visually. Okay. Duly noted. Let me see. So let's talk about, before I get too far away from addition, I just kind of wanted to show you multiplication with this kind of thing. What were some of the properties of addition that we learned before? Some of the basic ones were like
Commutative.
commutative. So are fractions addition, is it commutative?
Yeah.
So let's see. We kind of have to prove it, but the nice thing is it inherits the properties. Because for one thing, can you guys see really quick? Can you guys see? I know I don't have any numbers up here, but can somebody tell me what this guy is missing that this guy has on the bottom? A D. I love it. So purple is a little evil, but that's too bad. They give this guy a D. And what about this guy?
A B.
B. Now they're both the same, so I can add them. Now the top, what's A times D and B times D? Those are both whole numbers. And we already know whole numbers are commutative. So therefore this equals this. It's a long way to go for this, but stay with me. So therefore this is true, which means this is true. So that is how you prove that A over B plus C over D is equal to C over D plus A over B. We didn't know if fractions were commutative, but if I rewrite them with the same denominator, I end up with whole numbers on the top, and those are commutative right there. Not ground shaking. So fraction addition is commutative. What about associative? I could do something very similar for associativity, right? So fraction addition is associative. What did associative mean? In what way? Is it pretty cool with this, by the way? I see a lot of you guys squinting at this poor little dude.
There's a weird glare on it.
Oh, I'm sorry.
That's how it is.
Yeah. What's associative mean?
What you do to one side, you have to do on the other?
No, that's when you move the.
Parentheses. Your parentheses get up and move and it stays the same.
Oh.
So I can do something very similar for associativity. It would work because whole numbers are associative under addition. Okay, like it. So what this ends up doing for us then, for example, knowing that these properties exist. If I had to add these fractions together, 2/5 plus 7/19 plus 3/5 plus 12/19. Why am I not going to start here? You know, let me get elected denominator. God, this guy sucks. Give me this problem. What are you going to do instead? Say again?
2/5 plus 3.
Yeah, so I'm using commutativity, right? And does anybody remember what this is called? Starts with a C. It's not sort of, but yeah, I kind of appreciate that. But looking at them as just numbers. There's certain kind of numbers. They are
They make the 10.
simpatico. They're compatible. So So these two are compatible because what's 2/5 plus 3/5? Which is 1, and then what's 7/19 plus 12/19? 19/19, which is 1, so it's 2. Yay! Not immediately obvious at first, but when you have to add a bunch of fractions, you hope to God, oh, does some have like denominators already, number 1? And number 2, do some make whole numbers? That'd be awesome, right? So that's the same old thing about compatible numbers. 2 fractions making 1, they're compatible. So the idea that they're commutative is important, because otherwise they couldn't do that. What about the identity? What's the additive identity for whole numbers? 0, because identity means if I use the operation with this number, it maintains this identity. It doesn't change. So if I add 0 to a number, it doesn't change. The multiplicative identity is the number I multiply by, and it doesn't change. So multiplicative identity is 1. Kick ass. So the idea of identity is awesome. The word actually makes sense. It maintains its identity. So what about for fractions then? So if I add 4/5, what do I add to it to make it stay 4/5? Of course you add 0, but you kind of add that, yes? And of course, what does 0 over 5 reduce to?
0 over.
0 over 1, 0, okay. And again, this might not be immediately obvious to somebody first learning the idea of fractions, is that 0 divided by 1 is 0. 0 over 1 looks different than just 0, right? And why is 0 over 5 equal to 0 over 1? Why the shit's that true? Because if I divide top and bottom by 5, it's 0 over 1. Okay, maybe. So the identity is the same thing to God's. Let me see. If you had to estimate, and dear God, when you have fractions, you desperately want to estimate very often. So if I had to estimate what 3/4 plus 1 2/5, what do you think one way I could do to estimate what that is? Don't make it decimals, because that's the whole next chapter is decimals. So to estimate, I shouldn't have to do a lot of work. Kind of.
Ignore the 1 and just do it, because like the 1.
So can somebody just tell me what that is roughly? I mean, just 2/5 is a little less than a half, yes? 3/4 is a little more than a
A little
half.
over 2.
It's like 2.5.
So it's gonna be roughly 2, right? Maybe a little more than 2, yeah. It's roughly 2, do you agree with me? So to make this more formal, I could do one of our favorite things we've ever done in this class. I could do a range estimate. Right? But one of my favorite was, so I could do like anywhere from 0 plus 1 up to 1 plus 2. And if I average these, I get freaking 2, what we did just by observation, right? You guys semi with me? Or I could do something I kind of like better. Round that to the nearest half. That one's a little tricky, but it's a guess, but. So the nearest to half could be a half or 1. Now 3/4 just happens to be right in the middle. Are y'all with me a little bit? All right. Now think about it though this way. What's this to the nearest half? 2/5 to the nearest 1/2. Is 2/5 closer to a half, or is it closer to 0? Closer to a half. So I'm gonna make this go up to 1.5. So I should probably make this go down to a half. And then we end up with freaking 2. Yeah. So there is a process for fraction estimation. Take it to the nearest half, because halves kick ass. If I have to add a certain number of halves, that's awesome, right? So rounding it to the nearest half is nice. Or I could do this whole trick about just the range estimate, which is also kind of nice because I can make them whole numbers, which is awesome. But that range estimate's not really good by itself. Or I could just kind of eyeball it. This is a little more than a half, this is a little less than a half, so when I add them together, I should get a 1 plus 1 is 2. So it's not a ton of estimation here, but they do bring estimation back up for fractions, which makes sense with fractions. Fractions are not immediately obvious, but we can very often tell, is it close to this, is it about this?
For the first one, how you rounded it to a half, how come you didn't round up versus rounding down?
Well, the specific reason, 3/4 is directly between 1/2 and 1. I could have went either way. But I knew I was gonna take this up a little bit.
Okay.
So then I decided to take this down a little bit. Kind of to average things out. Does that make sense?
Mhm.
Okay. Okay, maybe. How do you tell very quickly if, like, is that below a half or over a half? Slightly below. One way to do it is if you double it, does it become 1 or more? If you double it, isn't it still less than 1? So this must be less than half. Do you see that? So the whole idea of rounding to the closest to half, you have to have a kind of an intuitive sense of, well, is it closer to a half? Is it closer to 0? Right? You guys kind of with me? Another way to do it is 3 plus, so what about 4/7? Yeah, so 1/2 would be in the middle somewhere, right? Is that all right? Yes.
So it's kind of possibly dumb question. Why can't you put like decimals as a numerator?
Just because of the way we define fractions. That's literally it. In general, could you do, we don't know decimals yet officially, but could I do 0.25 divided by 5?
Yeah.
I could. Mathematically, we know what to do here. Is this a fraction? No. Is this an okay thing to do and write? Yes. You just can't call it a fraction. Because by definition, a fraction is a ratio of whole numbers. Yeah, I like it. The most exciting form of thing is definition. So, sorry about that. These things happen. Okay. So, we've talked about mixed numbers before. So how in the world would I do 2 2/3 times 1 4/5 or whatever? Oh yeah, keep it that. If I try to do this visually, can you see how it's going to get kind of gross pretty quickly? Okay. Because I could try to do this. I could have 1, 2 for 2, 1 for 1. 2/3 gets a little bit freaky to try to draw, but I could have 1/3 and 1/3. And I could have 4/5. I could have a 1/5 and a 1/5 and a 1/5 and a 1/5 and that's it. 4/5. Okay. This gets a little bit weird.
A different symbol?
Huh?
You could do a different symbol too, for like the.
Yeah, so I could, let me make this a little bit better. So I've already got this established as 1, yes?
Yeah.
So I could do 4/5 would just be, like that thing truncated a bit. Right, if I cut it into 5 pieces, that's just 4 of them. That's 4/5. So down here, this could be that cut, so that's 2/3. So then this would be 1 times 1 is 1. 1 times 1 is 1. This would be 1 times 4/5. 1 times 4/5. Not 4, Jeff. You got it, buddy. You got it. And this would be 1 times 2/3. So then the only weird part would be, the only weird part, Jeff. 4/5, 4/5, 4/5, 2/3 would be this guy here. And that's where we could do like we did earlier. 2/3 times 4/5. So we could do 2/3 times 4/5. So that would be 8/15, of course. And then I have to add all those together. Oh my God. Right? So that is a visual way to do that if you so felt inclined. What is evil? What do you think a student might do incorrectly if they wanted to? So just to kind of finish this up real quick. That'll be 1 + 1 plus 4/5 plus 4/5 plus 2/3 plus 8/15. And then I still have to get an LCD and get all the stuff together. Is that cool? Okay, I like it. You guys stay with me. Okay. So that is one way I could do this. What is the direct computational way to do this? What sucks about mixed number notation? What is the bad choice we made about mixed number notation? What's in the middle of 2 2/3? What does that mean when I say 2 2/3? Does it mean times? Does it mean divided? Does it mean... Okay, is it decimal? Sure. I don't want decimal sign.
That's gonna be a plus, right?
This is an understood plus sign. So this literally means 2 plus 2/3. So of course, the way that we normally do a mixed number multiplication problem is we normally just change it into improper fractions, which is basically just doing what that's asking me to do, right? So instead of doing this whole mess here and getting LCD, I can just do the shortcut. So what's the shortcut? What would this become?
3 times 2 plus 2.
Good.
8/3. 9/5.
9/5, I like it. So then what do you get?
72/15.
72/15.
They drop it down to 24/5, and then 4 minutes.
So what do you, I'm sorry? Yeah, so you can reduce this.
I reduced it to 24.
Good. 7 plus 2 is 9, 1 plus 5 is 6, those are both divisible by 3, so they're both divisible by 3. Right, so that'll be 24, yeah?
Yeah.
And then you can make that into a mixed number. How we doing with that? Does this come back? How you deal with multiplying mixed numbers, the easiest way to, now I want you to notice what happened. In this notation, there's a plus sign, correct? And if I wanted to do this directly, I'd have to FOIL it. Do you guys see that? I don't want to do that. If I rewrite this in improper fraction notation, there is no plus sign anymore. It is this number times that number. There's no foiling. Say again?
The 8/3.
8/3, right here. 3 times 2 is 6 plus 2 is 8. Yeah. Or multiply by 3 to make LCD. 3 times 2 plus 2 is 8. Which explains the shortcut, right? So over here, you're cool with the 9/5? Okay, same idea.
It was just because one's easier. But, yeah,
Huh?
because one's easy, but yeah, okay, that makes sense.
Gotcha. And of course this, if you want to, if only it was 20, 5 would go into it. So that's another way to get to the 4 4/5 without having to do long division, right? Okay, I like it. Now if I were gonna estimate this, I could do like a range estimate. 2 times 1 is 2. 3 times 2 is 6, so it's gonna be between 2 and 6. So obviously that much is good, right? Okay. Let's see. Oh, good. Now, this one specifically didn't have anything good here, and what do I mean by that? Poor little problem. Why is this problem, even though it looks worse at first? Yeah, what are you gonna put, Jeff? Sure. Got it, buddy. Let's do it. Yeah. Sure. Okay. What can you do with that problem? Well, that problem's pretty gross. It just is. But am I gonna just do 250 times 27, get that big ass number? And then 18 times 50, get that big ass number? Is that what I'm gonna do? And then reduce those huge freaking things? I don't wanna do that. So what do we do in this case, and why are we allowed to do it?
Can we divide 50 by 50 and 250 by 50?
Yes. So 50
Divide by
goes into 250 5 times. And of course, why am I allowed to do that? Because if I did multiply them together, commutativity says I could do this. And then I've got this fraction and this fraction, right? So instead of doing all that craziness, as long as on the bottom and the other one's on the top, I can reduce it. So what happens here? Well, how far apart are 27 and 18? Seconds? 9. Try that. Does 9 go into both? Yes. So if a fraction is going to reduce, it's got to be a factor of how far apart they are. We talked about that before. When I say it like that, it might sound kind of weird, but these are 9 apart. So if it will reduce, either 9 or 3 will go in. So try 9 first, and sure enough, 9 works. So then I get 15 over 2, cool, which is a mixed number? 7.5. So the way to do divided by 5 is 14 divided by 2 is 7, and they have an extra 1 over 2, so 7.5. Yeah, I like it. Okay. We already applied this idea, but I didn't really call it its official name. So, remind me real quick, what is the job of the additive inverse? Have we talked about additive inverse yet? Probably not, because we haven't said that negative numbers exist yet. So when I say when I say the word inverse, what does that mean to you? Does it mean anything to you? Inverse?
The same number, just distance from 0.
Not quite.
If it's negative, it turns to positive.
Good, so there's an additive inverse, which is if I have like positive 7, it's additive inverse is negative 7. What is 7 plus negative 7? 0. So the job of the inverse is to take it back to the identity. Let me say that again. So what is the inverse of 3? The additive inverse of 3?
3.
Negative 3.
Negative 3.
Because 3 plus negative 3 is 0. And 0 is the additive identity. Are you with me? So inverse is the opposite of the number in some way. Additive inverse is the opposite sign.
Is
Multiple.
the additive identity always 0?
Yes, definitely. By definition, additive identity for real numbers, for whole numbers, is 0.
I think of it as like its alter ego, like the negative's like the evil side.
Oh, I see. All right. Like the parallel, like they have mustaches. Is that what it, they have little goatees? Like, so negative 3 is just 3 with a goatee.
It's like the disguise.
So when they see each other, they annihilate each other. Ah. Huh? Spy versus spy? No way. That's an old. I even played the video game a million years ago. All right. There was a video game for Spy versus Spy. Yes. Multiplicative inverse. Remind me, what's the multiplicative identity? What do I multiply to maintain something's identity? 1. So the multiplicative inverse is the number I multiply something by to bring it back to 1. To bring it back to the identity. So if I have 4, what do I multiply it by to make it 1? 1/4. Beautiful. So what's another name for multiplicative inverse? Starts with an R.
Reciprocal.
Reciprocal. Yeah. So what's the multiplicative inverse of 7/11ths?
11.
Holy shit.
Geniuses.
Wait, what's this called?
Multiplicative inverse. So 11/7 is the opposite of 7/11ths in a multiplicative way. It's not the opposite in an additive way. What is the additive inverse of 7/11ths?
4 11s. 0.
What's the opposite of 7/11ths?
Negative.
Negative 7/11. There we go. So let me say this again. No matter what the operation is, the inverse is the number I would operate with to bring me back to the identity. What is the additive identity? 0. So the additive inverse is the number I add to bring it back to 0. What's the multiplicative identity? So the multiplicative inverse is the number I multiply to bring it back to 1. Of course, we have better names for this. We just call that reciprocal. And we just call this the opposite sign. We just call it the negative. Now, we normally just call it the opposite, but there's officially 2 kinds of opposite. Okay. Oh, okay. One of the coolest things. Okay. Let me get us to a place where I can. Yeah, okay. We're almost here. Why, if I ask you what this is, obviously we're doing division. Why is that not horrible?
Because you can divide two fractions.
So again,
You can divide fractions.
yeah, this is, what's one way to approach division of a student's first learning division period, like their first learning division? So if they want to figure out what 8 divided by 4 is. Sure, how much of this can go into this, but even before that, how do you build it off of the idea of multiplication? If I want to know what 15 divided by 5 is,
What 5 equals 15?
yeah, 5 times what is 15, right? The missing factor approach, yes. So here, I can think 8/9 equals what times 2/9?
4.
4, okay, good. So one way you could use for division of fractions is actually the same thing we used before for division of just numbers. You can think missing factor approach. That quickly becomes untenable. If the fractions are worse, that's not something I just go, well, of course 7/13 times 11 over 873. No, I'm not going to do that in my head. So here's a kind of a cool visual. Let's see if how I create this. Let's see. 8/9. Why did I pick 8/9? 1, 2, 3, 4, 5, 6, 7, 8. Sure, okay, that works. 8/9. There you go, good job. How many 2/9? And this is going back to what somebody said earlier. How many 2/9 are in 8/9? So where's 2/9? Isn't this right here 2/9?
Yeah.
So how many of those are in there?
4.
Frickin' 4. That's crazy. Isn't that nice? That's a really beautiful visual. Now, of course, 8/9 and 2/9, they go together. So that was an easy one. So 1, 2, 3, 4. There's 4 of these in 8/9. So 8/9 divided by 2/9 is 4. So obviously, if the bottoms are the same, in fact, can you guys see a generalization I can make? If the bottoms are the same, what's the answer going to be? How did I get 4? What did I actually do? So this would be, yeah, A divided by B, kick ass. Yes,
Can't we just
we're building up to it.
change it to multiplication?
Yes, we can. But we're talking about visual, conceptual understanding of division versus computational process, right? Yeah. But I mean, even here, if I multiply by the reciprocal, what do I get? What do the C's do? They cancel, so I get an A or a B star. But before I even know that, I can make sense of what that's going to be. If the bottoms are the same, everything should be a little easier. It's when the denominators get different that makes everything a little worse. So what if? Before I forget, this one works for this. This will quickly not work. But just to remind you guys, what is division fundamentally defined to be? Multiplication is repeated addition. It's repeated subtraction. So if I subtract 2 9s from this, how many times can I do it? Until I get to nothing. 1, 2, 3, 4. So again, that's the answer is 4. That quickly becomes no good, but it works for like if the bottoms are the same. Same idea. Okay. Where's my example? Oh, there it is. Yeah, that's the same idea. Yeah, that's a little bit crazy there. There it is. There it is. So, what if I had 2 divided by a third, and I want to do that visually? Whenever I do division, like somebody said earlier, you can ask yourself, how many thirds fit into 2, right? So what's an easy way to represent 2 that I'm going to be able to cut up easy? So here's 1, 2, yes? Cut it up into thirds. So how many thirds are in 2? 6, yes. Cool. So you guys try this. So in keeping with the math teacher code, I'm going to give you a worse problem. 3 divided by 2/5. Try to do that. I am an evil person, so it's better to know that now. What I'm going to do with, so there's 3. And then for each one of those, I want to do what?
2 fifths.
Okay, so pretend like those are evenly cut. So now I want to count. Yeah, every 2 of them. So there's 1. There's 2. 3. Is that cool so far? 4. 5. 6. 7. And how much of a 2/5 do I have left? I have a whole 2/5 here, right? And another whole 2/5 here, and another whole 2/5 here. So what's this? Half of a 2/5. This is 1/2. So this should be 7 and a half, or
15 numbers.
15 halves. Yes. So let's check it. How do I do that directly? We know how to do this. Yeah, this will be 3 times 5 over 2. 15/2, which I can write as 7.5 if I want to. By the way, before I get too far away from this, do you see how this example we did up here, how does this picture represent multiplication? This picture right here. Because you're counting how many thirds there are, right? So there's 3 of them in this one block. There's another block that has 3 of them, so there's 2 times 3. And isn't that what this becomes if I multiply by the reciprocal? So there's a visual representation of something that they would identify as multiplication, yes? It's another verification that the way to handle division of fractions should involve multiplication somehow, because it becomes a physical multiplication problem. Okay, maybe. There's 3 parts here, 3 parts there, 2 times 3 is 6, 6 parts total. Okay, maybe. Of course, this one is a little bit harder to do that with. I want to show you something a little, well, you know, a little weird. See what you guys think about it. If I have 16 27s and I want to divide by 2 9s, I'm not even sure if I want to show you that. Well, I'm going to show it to you anyway, just in case this comes up. Here's an exceptionally weird approach to this. I'm allowed to multiply top and bottom of this fraction by whatever the hell I want to except 0. So I'm going to multiply by 2 times 9. I'm going to do the same thing on the bottom. So can I just divide this straight across now? 16 times 2 times 9 divided by 2. 16 times 9. 27 times 2 times 9 divided by 9. 27 times 2. And then I can reduce this stuff, yes? That's trippy. I want you to notice something. What is the point of this, dear God, Jeff? Do you notice what happened when is everybody cool with this 2 dying because I'm dividing? Is that cool?
Yeah.
16 times 2 times 9 divided by 2, the 2's cancel. 27 times 2 times 9, the 9's cancel, correct? Here's 16 and 27. That was my original problem. What else is up there?
2
2 9.
So isn't that the reciprocal of 2 9s?
That's why I was confused of why you did that.
I know. But again, this is another way to show why multiplying by the reciprocal actually makes sense. If I give top and bottom both of these numbers, then they can directly cancel, and then it's kind of nifty. Whatever's left is actually the reciprocal of what was there to begin with. Okay. Blah, 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 blah. Yeah, good. Okay, I think I'm almost, yes. Oh, this one little thing here, yeah, okay. And then I'll show us some videos and then we'll head out. Yeah, what do you guys think about this here? You wanna, yeah, okay. I'm gonna put something different there, but it's all right. Yeah. Do it like that, it's better. So what can I use here to do this easily? If If I use PEMDAS directly, then I have to do 25 times 1/4 first. Do you want to do that? You want to do 25 times 1/4?
Distribution.
Why does distribution not work here?
Because there's nothing.
There's no addition. Distribution is
That makes sense, you're right.
across addition or subtraction, yeah. Okay. So let me give you a hint. Commutativity, associativity, compatible numbers. What number is compatible with that 1/4? 16, because 4 goes into 16, yeah? So I can do this. That's associativity. And what's 1/4 of 16? That's crazy. And then what's 25 times 4?
100.
100. So that's 2 compatible numbers in one problem. Yeah. Oh yeah. Why is this division problem easy? This should be an easy division problem. Why? Because 3 goes into each piece, yeah? 1, 1, 08. Do you guys see that? So that's tricky if you use it all the time. I did it earlier with that problem. 11, 11 divided by 11 is 1, 01.
How do you know when to add the zero?
Oh, because well, you have to kind of know this kind of a thing, right? You have to keep this in mind. So if I put a 1 there, there'd have to be an O so that 11 goes into 11 once. So building off of that knowledge, I know what to do with that, yeah. Plus I know the answer can't be 11 because 11 times 11 is not 11, 11, yeah. Okay. Let me not keep that up there. All right. So watch this. What is 18 6/7 divided by 6? Is each piece of this divisible by 6? Yeah, what's 18 divided by 6? 3. And what's 6/7 divided by 6? Okay, cool. It's not always going to happen. But when it does, you want to be ready because that makes it easy. Like it. So any questions on that? We just finished chapter 6. That's what happened. I'm going to show you a few videos and then we're going to head out so that I can get all the way up to Rancho Bernardo.